Okay, this is Sherry Yang, CST320. This is week 5's lecture. And week 5, we mostly wanted to do a quick review of the grammar modifications that we did in week 4 and start looking at the recursive descent parser. We did not get through the first and the follow sets, which will be part of week 6. There is a test week 6, February 8th, Monday, covering homeworks 1, 2, 3, and lab 1. But I will be lecturing the first hour of Monday and covering the first and follow sets, and there's a little exercise for you to do. And then we'll take the rest of the time for the test. A checklist of the items you should know for the test have already been put up in Blackboard, so you should take a look at that. So last week we had a grammar example, the E plus E, the E times E, which was the grammar itself was ambiguous. And I said I will try to fix that this week. As you can see, by fixing it, I'm also adding the plus, the minus, and the divide, which is the same operator precedence. So it's really the same rule. By fixing it, I actually had to add 2 more non-terminals, the T for term and F for factor. So we have expressions, term, and factor. By breaking it out this way, it forces the pluses and the minuses to be match at a certain point, and it forces the times and the divide to be matched at a different part of the grammar. So this gets rid of ambiguity. Also took care of the operator precedence. So I'm not going to have the plus and minus before I evaluate the times and divide. And so this is a trick, our technique rather, that we handle all operator precedence. So that's why we don't just have one E rule. Usually for expressions, we break it up into many, many different rules. There are unary expressions, there are binary expressions, there are, and then that allow us to put in the operator, evaluate the operators in the order that they're supposed to be evaluated. As you can see here, the I equals A plus B times C, that input string got mapped into a parse tree. And this is, again, this is called parsing. We're taking a grammar, we're taking an input, we'll try to match them together and see if they fit. And in this case, there's only one way that this is going to fit. There's only one parse tree. So we got rid of the operator precedence. What we did not get rid of was the left recursion. Notice the E goes to E plus T, E goes to E minus T, and T goes to T times F, and T goes to T divided by F. That's called left recursion. And the problem with left recursion for the top-down parser that we're doing is that we can't, the technique itself, we need a token. We basically need to be parsing things rather than wait till the very bottom of the tree before we grab that first A. So the A, as you can see here, is like way on the bottom. So we need to be processing tokens further up on the tree. Since we're coming down from the top, the S goes to, we're starting from S. So in class, we did, which will not be on the video, is we actually had a little in-class exercise where we changed this grammar into a non-left recursive grammar. So if you missed that, come see me or see if you can get the notes from someone in class that show an example of what it looks like if it's non-left recursive. And we'll come back to this grammar over and over again because this is a very common way to handle expressions in our programming language. So you'll get an opportunity to see this again. Homework 2, we mostly deal with, okay, now we have a language, let's come up with a grammar. And we did not start from scratch. We had Mini C or Lua or the Homework 1 Pascal grammar as a guide, which we can build on. But you should be able to, and this will be on the test, so you should be able to take any language, in this case, very small language, and try to come up with a grammar to describe the syntax of this language. So here I have a very small language. It doesn't have a name, but it's very much Lisp-like, where we could define functions like the add, and we could how to get anything done in the language is the very first parameter in that expression, like the add and set and negate and plus and print and so forth. Those are what's called commands or operations. And then the rest of those are parameters. Some commands or operations takes 2 parameters or more. Or in this particular case, I'm limiting it to only up to 2 parameters. In the full language, I may have more than 2, or no parameters, or 1. Okay, so my language should be able to handle that. And let's take a look. So here's an example grammar where what is a program? Well, a program is just a bunch of statements. So statement followed by more. And statement could either be a function definition or could be a function call. Yes, these are both unit productions. We talked about unit productions. And we could see here, this unit production allow us to separate the categories. So you have function definitions, you have function calls. So let's start with that separation and then decide what a function definition looks like and a function call looks like. Doing it this way, yes, it makes the grammar a little easier to read, but makes the parser will have to work a little harder because I'm just looking at one token. I cannot tell if it's going to be a function definition or if it's going to be a function call. In this case, is further complicated by the fact that everything starts with the open parenthesis. So everything starts with these parentheses. So you can't really tell till you get to the second token. So that speaks of the need sometimes for left factoring. Well, everybody starts with the open parent, so let's just start with that. And after that, the second parameter will tell me something about what to do. So it's a very simple language, as you can see here. The parameters could either be ID num or lambda. So that means I don't need to have any parameter, or I can have 1, or I could have 2, up to 2. So here's what will be a sample grammar if I give you a very small language. All right, so now we're going to look at this technique called recursive descent parser. We need tokens. Okay, so what came out of your lab 1 should be a list of tokens. Tokens should be a pair of value and a type. Main, for instance, is the value, and main is an ID. And that ID is what's going to show up in your grammar. So let's back up a little bit to this previous grammar. Notice there are some keywords like set and negate and print, and there's some operators like plus, minus, times, divide, and those themselves are tokens. There are keywords like define function, that's a token. But there are user-defined identifiers like main or add or whatever the name is. Those are IDs. So ID showed up in the grammar. So when we're parsing through our tokens, and that's why we tag them, so any user-defined name is ID. And that's how we make match with the grammar, because main itself will not show up in the grammar, but ID will. So that's why we keep these pair of values. And so really IDs and numbers are the ones will look to the token type. Everything else will look to what that token is. I know on the slide here, I said the open print is a symbol and bracket is a symbol, but open print is just that. It is a symbol, but yeah, but it is also just an open print or a bracket, open bracket, or int is just an int, and void is just a void. So that's what's going to show up in the grammar. So we're going to take a list of tokens, and our first technique for a top-down parser is called recursive descent. And recursive descent, so if you didn't have a list of tokens from your lab 1, or you did not want to add this directly to your lab 1, you want this to be a separate program, all you have to do is dump the tokens to a file and then have your recursive descent parser read them back in from a file. It's a lot easier now. You don't have to parse. Everything is there. You just have to read it in and load it into an internal data structure. A vector is fine. A list is fine. So just read them in and work with them. What you need to have is ability to go back and forth in your token, what I call token buffer, and this could be a list or vector or whatever. So as I'm processing each token, I need the ability to say, okay, give me the next one, give me the next one, give me the next one. But also, if I have to backtrack, remember we talked about what if there are two rules that are very similar, like if statements. You can either have if with the else, or you can have if without the else. Okay, so what if you pick the wrong one? Now you have to go back and pick the other one. And that's where left factoring comes in. If you left factored those two if statements, one with the else, one without the else, then you wouldn't have to backtrack. But not all, you probably won't be able to left factor everything, because it really gets complicated. So say if you did not left factor everything, then you had to go backtrack, then your token buffer, whatever data structure you use, you need to have a pointer, you need to have an index, whatever happens to be iterator, to be able to go back to where you were when you started this rule. So you can go back and then start over, backtracking. So this is important. So the ability to say, what's my current token, but also what is, if I had to go back, what did I start it with? But also that those pointers or iterators or indexes will also tell you how many tokens made up this rule. I'm looking for one of these rules, like a statement. Well, how many tokens did I pull off? What does this statement look like? So I will be able to print them back out again. So that's important as well. So there are two types of rules, one with lambdas, one without lambda. So as you can see here I have a field, which is a bracket, expression, bracket equals expression, or name equals expression. The name here is like IDs, user-defined names, or an expression, maybe an algebraic expression. And then the function name 2 here starts with a dot, name, function name 2, or lambda. So the field does not have lambda. Func name 2 has a lambda. For recursive descent parsers, every single rule becomes a function, a bool function. So field, bool, field, func name 2, bool, func name 2. And it is a bool. What is it going to return? True or false? Did I grab a field, or did I match a field? Did I see a func name 2? Yes or no? True or false? That's what the parser is doing. For part 2 of lab 2, we will go in and we will add some meaningful messages, error messages, or we may want to print out, well, yeah, we said that I just matched a field, but what were the tokens that made up the field? I can print that out. Having the indexes or iterators into my token buffer allows them to see what tokens So here, we're not going to read the tokens in from the file one at a time, obviously. We want to load all the tokens in. And we're not talking about huge programs, but even with the slightly bigger programs, I think we're willing to pay the price for the memory for efficiency. So we will have a function for every single rule in the grammar. For the non-lambda rules, you either match or not. Okay? There's no other choice. The lambda rules tend to be a little trickier because lambda means the rule doesn't actually match any token. So if you don't have any lambdas, that means every single token or every single part of that rule needs to be mapped to a token. But lambda says it doesn't match anything. So you're not pulling any tokens off the tokens list. So the caution there as you manipulate lambda rules, you don't want to go to the next token yet. You haven't processed the current one because it didn't match anything. So that's a caution because it's very easy to keep going and then you miss a token along the way. And because it doesn't match anything, it doesn't mean that it's wrong. It just means I don't need this rule. If this was a if else, well, I didn't have an else. Well, that means I didn't need the else. Move on to the next token or the next rule, the next statement. So I might be looking at the token for the next statement already. See if I have a while following an if. Well, I didn't have an else. So I'm looking at the while now. I'm ready to go on. But so that means the else part is lambda. It's okay. I've still matched the if just fine. It's just I didn't have an else to go along with it. So in this case, one way to handle it is just to return true. Let the next rule handle. What if there was an error? Well, let the next rule handle it. Error will pop up. Error will sort of get caught somehow. Right? So the lambda rule just will always return true. So here's an example. And so here's two simple rules. S goes to A, S, B, or C. So notice the pseudocode says, when I'm looking for the token A. If I didn't have the token A, then I'm going to go look for the token C. If I didn't have token A or C, well, it's not S. Something else. So S returns false. But if I had the C, I'm done. I'm only looking for a C. I don't have anything else. That's the second rule. But if I have A, then I'm going to continue. Is the next thing a S? Notice the recursive here. Recursive descent. S is going to call itself. So how is it going to keep track the B's with the first A? Well, the recursion takes care of it. Here I have a stack, not an explicit stack. I didn't push the A onto a stack, but because the recursive nature of the call, by the time I'm done with the S, when I come back, there's a B waiting for me to be matched. So A, S, B, they get pushed onto the call stack as you make recursive calls. And as you finish and return from the recursion, kind of unravel that stack, so it will pick up the B. So it doesn't matter how many A's I have. Every time I call S, it's like I'm remembering that I need a B to go along with it. Okay. But anytime it fails in that, see if I have AS but not a B, then of course it will fail. So as you can see, with the recursive descent, your functions tend to get very big. If you have multiple parts to a rule, you got to check every single one of them. What if you have lambda? So we'll do the same thing for the ASB on the top, but what if it's not an A? Well, that means I didn't need it. I couldn't use it for S. Maybe I could use it for something else, but it's not S. Okay? In fact, notice the S in the middle, the ASB. At some point, I'm not going to have any more A's. And that's when the S gets dropped to lambda. Then I start picking up the B's. Correct? So at some point, I'm going to run out of the A's. I'm just going to have B's left. I'm trying to match the B with the S, and obviously there's no rule in S that starts with a B. So that tells me, yeah, I'm going to use the lambda because I'm done. So this is actually good. If I only have B's left, that's good. Well, if I have like C's left, well, it's not. I'm still going to return true here for lambda. It still says I don't have any rule that match that token. Well, make a return true for lambda, and because you need ASB, say if you only have C's left, that will get picked up when you try to match a B with a C, and obviously they don't match. Then it will return false at that point. So yes, errors will get caught by returning lambda. It doesn't hurt anything. I think I just highlight the fact, yes, that we are using this is a push down automata, which normally will have a stack that we push things onto, but because I have the ASB and the recursion actually take care of the stack. So I already talked about that. And when we have unit productions, take a look at this. You have a bracket, a name, or an expression. Expression is a unit production. I don't know what expression needs. I have to go look up the rule for expression, see what it starts with. What tokens? Does the expression start with a bracket? Does the expression starts with a name? I don't know that. Okay, until I go take a look at expression. That's why sometimes we want to get rid of unit productions so I can line up all the rules and see, oh yeah, they're all there. So then I can have, I could do left factoring if needed. Okay. So because I don't know what expression is, I might be going down a path like bracket, expression, bracket, and then run out of tokens for that rule. Then it doesn't match the first one. Then I have to try the second one. If the second one doesn't match, then I have to try the third one, which means I have to move the tokens all the way back to where I started this rule. And that's what I was talking about with the backtracking. I said here you need to put the tokens back, but no, really what you need to do is move your iterator, move a pointer if it's to a list, or move an index if it's to a vector, to the beginning of that rule. So every single function, every single rule, as you enter it, you have to remember where you are in the tokens, because you may need to go back to that point and try a different one. So just kind of keep that in mind. And lambdas, of course, doesn't actually remove any tokens, so don't advance tokens. Keep at the current one. Don't go to the next one yet. Okay, that's a very common mistake. I think at this point, this slide just says that even though the big B, C, and D is not a unit production, sometimes it's a good idea to have all of your rules start with a token rather than a non-terminal like big B, because I don't know what big B starts with. Say I have a rule that starts with a little a, I have a rule that starts with a little b, then I have a big B. Does big B also have little a's or little b's? If so, then I may have to backtrack or left factor to avoid backtracking. So sometimes if you can, try to clean up your grammar rules so they all start with a token, or at least they all start with a unique. So if big B does not start with a little a or little b, then you're fine. You can still go to big B, have big B handle whatever it needs to be handled. Okay, but if big B starts with a little a or little b, then you run into the issue of backtracking because they're no longer unique rules. So this slide just says, yeah, even though T and F are not, TX and FY are not unit productions, I might just want to expand them out. Just make them into starts with tokens. That's always a good idea. Um, I think at this point, I'm going to kind of stop the slides here. And this set of slides actually go with the idea of the first and the follow set, which we're going to take a look at in week 6. By this point, I actually like to switch over to some sample code. I gave you some sample code, and I hope this is big enough to show up in the video. I gave you some sample code. It's not a complete project, so when you try to build it, it's not complete. You still need to take care of the tokens yourselves, how to load the tokens in. I wrote this program long time ago for a different class. I didn't have my parser in a class, a C++ class. I probably should have it in a class rather than a C-like, because I think it makes it easier. If this was in a class, then I could just have my data member to be the list of tokens. But as of now, I have a global tokens a vector and also a global iterator into that tokens vector. This particular grammar has 2 rules. S is either ASB or big A, and big A is little c or lambda. Okay, so one has a lambda, other one does not have a lambda. And this tells me that I need 2 functions, S, A, both bool. And S function has 2 parts. S function needs to take care of either the A, S, B, or it needs to do the big A. Oops, sorry. The big A. So if it's big A, then then you found it. Or if it's ASB, you found it, otherwise it fails. So it's just a big nested if and else. So you do have this code, so you can follow it probably closer, easier. Notice I always remember where I am by setting a temporary iterator. So this iterator tells me that, when I started looking to parse S, I actually started with this particular token. So if I went down one path and I didn't find it, and so I have to come back and do another path, then I will make sure that I backtrack to temp, and then so I don't lose any tokens. And I always check to see if I'm in the file also. Just because I'm looking for ASB doesn't mean that the user actually gave me enough tokens. So if I try to look for something, I'm already at the end of the vector, then I might get a problem. I might have problems. So always look before you grab the next token to see if there's actually a token to be grabbed. So this simple file only has the S and A. The next file is called the cparser.cpp. This one handles the header for a typical, like a C-like language, function declarations with parameters, and in terms of statements, it only has return statements now. So it's a very limited grammar, but even for a limited grammar, I'm looking at, 12, 13 functions. And in these 12 or 13 functions, it handles, so this is my tokens list. So this is how I read them in from a file. So I have int main, open paren, close paren, bracket, int x, comma, y, semicolon, double z, semicolon, return x, semicolon, close bracket. This is my entire test input. Okay, I read them in from a file and load it into my G tokens vector, and then I just work with it. And every single rule, like decorations and ID list, param, data decoration, statement are all bool functions. And I even put a rule above each function so I know what I'm parsing. And so the format is almost exactly the same for every single function. I remember where I am with the temp. So if I backtrack, I can come back to that point. I check it, make sure I still have tokens left. And then I just go follow each rule. What am I looking for? Okay, so am I looking for an ID, followed by something else? Well, just keep looking for each token. Either you find it, you return true, otherwise you return false. So it's almost exactly the same. It's just some functions are longer than others because there are multiple parts to it. You got to check for every single part. And then if there's a lambda, you just return true for now. Okay, so this is in a zip file that I gave you in Blackboard. You can download it. You can take a look. This is how you could set up your lab too. For the first part, I just want yes or no. Did it parse all the way through or not? And don't try to do it for the entire program at once. Okay, so your main, okay, is either going to call the very star symbol, that function, or it's going to instantiate an object and have the object call, right, invoked the star symbol. So in this case, program, or in the previous example, S function. And if that whole thing returns true or false, your main just had to report that. Yep, the thing parsed, or nope, it didn't parse. We're not going to write any error messages. We're not going to, if it did not parse, it's just going to stop. It's not going to recover from the error. It's just going to stop. As soon as it hits the error, done. Everything is going to return false and comes out all the way back. Remember, this is a recursive call, so you still have to return to the caller all the way back to main. And that's it for part A. For part B, I'd like you to put in error messages. I'd like you to print out what you parse. When you say, yep, this thing is the parameters, but what were the tokens that made up the parameters? Also, I'd like you to utilize the symbol table to put information in. So if you're declaring int x, well, I'd like the x to go into the symbol table. So later on, when you try to assign x to something else, first of all, you need to check it, make sure x is declared. And also, if x is the right type. We might deal with the types later in the later lab, but I definitely want to deal with whether that symbol has been declared or not. So, so that's lab 2. And week 6, we're going to revisit this idea of looking for certain tokens. We try to modify our grammar so I only have one token look ahead. That is, I left factored it. I try to minimize unit productions so I can always work with tokens. And for any particular rule, let's take a look at this rule, for instance, this param2 that's on the screen. If param2 does not start with a comma, it is not a param2. So either it's going to be lambda if it doesn't start with a comma, or if it starts with a comma, it's going to be, right, that's going to be that at least gives me a chance to check the rest of the rule. Okay, so that first token is very important. The first token tells me, if it's not the thing I'm looking for, well, don't bother. It's probably not that. So just return true for lambda and move on. Unless it's a comma, then I'll continue to check. Okay, so week 6, we're going to talk about this idea of the first. What is that first token? If it's not in my first token set, well, don't bother. It's not there. It's not going to match at all. And because I have lambdas, I'm also going to be looking at something called the follow set. What should come after me if I'm not a comma? Okay, so that will allow me to maybe return false sooner rather than always return true for lambda and have the next rule deal with whatever error, if any, is there. Okay, so that's really week 5. And we'll come back, pick up the rest of these slides for week 6, and then continue with our first and follow.